Earth Day, and but we're going to talk about Earth core today. And this is our second seminar on the series of the Earth core. We started with Earth core formations, and it's my pleasure to introduce Jackie Lee today, and she's going to talk about, I assume mostly the composition and broadly how we come to this compositions and constraints and uncertainties, and as well as some very recent study focus on the composition of the carbon content in the core. So we're very excited about the opportunity to discuss this hot topic, and there will be some general question after the seminars, and then the postdoc should stay on and talk to Jackie separately for about half hour, 40 minutes, depends on how the discussion going. And then Jackie is going to come back on 1:30 for a more in-depth general discussions. Whoever is interested and should sign on to the same Zoom link, and so you will have plenty of opportunity and discuss the topic and as well as questions. And Jackie did her PhD in Harvard University, and then subsequently spent almost 5 years at the geophysical lab, and then moved on to University of Illinois for several years, and eventually she settled at University of Michigan as a professor there. And Jackie can take over.
Thank you, Fei, for the introduction, for the invitation. I'm very excited to have this opportunity to have a virtual seminar with many people I know and some people I haven't met before. Fei said I stayed for almost 5 years. I actually stayed for more than 5 years. Anyway, so Fei told me to give a broad overview of the composition of the core. And today I'm going to share with you 2 recent work I did. One was published earlier this year is a review article on Encyclopedia of Geology. And that gives a broad view of what we know about the Earth, how we know it. And the second one came out just this month and focusing on the carbon content of the core and what we can learn from it about Earth's accretion. So we want to know the composition of the core because the core takes up more than half of the Earth's radius. It extends from about 2970 all the way to the center of the Earth. It accounts for 1/3 of Earth's mass and 1/6 of its volume. So the core plays a vital role in Earth, a dynamic planet. The very rigorous convection in the outer core gives rise to the magnetic field. And we know that this field protects life on Earth, also generate the spectacular aurora, which is listed as #1 on many people's must-see kind of a plan. The heat hidden in the core also is important for drive the mantle convection and the plate tectonics. All those mountains, volcanoes, and earthquakes that we experience on the surface have the roots to the energy stored in the core. So the composition of the core is determined by how the Earth accreted and differentiated. So the knowledge about the composition will then give us constraints. Wow, the timing is not great. We have the long mile outside. I cannot do anything about it. So the composition, once we know the composition, we will be able to say much about how the Earth formed and differentiated. So now, throughout most of human history, the composition of the core remained an enigma. Enigma is defined as something that is mysterious, puzzling, difficult to understand. Even though we have very sophisticated instruments, especially EPL, we have the eProbe, SIMS, all kinds of things, but we don't have a sample to measure. In fact, for thousands of years, we don't even know the size and shape of the core. So here I show two speculations before seismology told us about what the core looks like. So back in 1644, the French philosopher René Descartes depicted the interior structure of the core of the Earth. So here is the atmosphere, ocean, water, and the crust layer as E layer. The C layer is supposed to be the core. And I imagine underneath is also the core. If you look at the solid part of the Earth, the core takes up an enormous extent according to Descartes' model. And then about 200 years later, we have this famous French writer, Jules Verne, who was famous for writing 80 Days Around the World, also the journey to the center of the Earth. In his picture, the core is much smaller, but more dynamic. It looks like a flower petal. So that's the extent of knowledge or speculation before, just about 100 years ago. So the core, the outer core, the boundary, core mantle boundary was defined in 1906. That's just over a century ago. It was based on the observation of the shadow zone, especially the S-wave shadow zone by Richard Oldham. So if you look at this drastic change of the shear wave, totally disappear core mantle boundary, tells us where the core mantle boundary is and the core is molten. We also have a significant decrease in the compressional velocity, and that tells us about the density of the core. So the core is very dense. So this was the discovery made in 1906, and 30 years later, Ingo Lehmann, through very detailed analysis, revealed the existence of a solid inner core. And my own knowledge of the solid inner core, I can remember very vividly when I was a graduate student, I was in a bookstore, Wordsworth in Cambridge, run into another graduate student from philosophy. And he learned I'm a geologist. He said, why is the hot center of the Earth solid? I said, really? I did not even know it was solid. I thought it was all molten. And I think that question somehow, together with my fascination about rain, snow, all these change of state, probably seeded my interest in phase transition, understanding how it happens in the Earth and in the universe altogether. So in 1981, we have this classical paper by Dwonsky and Anderson, the Prem model, which gives us the ground truth to basically determine the composition of the Earth. But of course, seismology and geophysics, they don't say anything about chemistry. We need other data to know what the core is made of. So the early attempt is based on analogy to meteorites. We have chondritic meteorites, iron meteorites, differentiated, undifferentiated. This approach is basically based on mass balance. So if we think about the bulk Earth, it's basically the two parts, the core and the bulk silicate Earth. The bulk silicate Earth includes the crust, the upper mantle, and the lower mantle. Now, we don't really know what the bulk Earth is made of, but we can use chondritic meteorites as an analogy. Don't really know what the bulk Earth is made of, but we do have access to the crust and some of the xenoliths brought up from the mantle through magnetic eruption. And then we also can speculate about the core being mostly made of iron based on iron meteorites. So this mass balance kind of approach gives us a pretty good idea of the main composition of the Earth. Iron makes up more than 80%, but there's uncertainty of at least 5 to 8% there. Nickel, we know the iron-nickel ratio relatively stable or constant, almost constant. It has a factor of 17. So we know the core contains about 5 nickel. And all the highly siderophile elements, if they are refractory like gold and platinum, they would be 99% or more concentrated in the core. The volatiles are problematic because the bulk earth differs from the chondritic, most of chondritic meteorites in that it's depleted in volatiles. And there is this famous volatility trend, which describes how the volatile abundance relative to chondrite and normalized to magnesium decreases as a function of so-called half mass condensation temperature. So this is the temperature when half of an element is in the nebular gas and half of them has already condensed into solid. And this model basically assumes that in the beginning, all the material, they've been heated up and become, all fully evaporated, goes into the gas. And then as the nebula cools down, different elements would be able to come down and then become available to accrete to Earth. But if you look at this model, this volatility trend has a lot of assumption built onto it. And some elements we just don't know. For instance, hydrogen is the most volatile elements there. There's very little constraint about what is bulk Earth hydrogen. Carbon, as I will talk about later, probably no. We cannot really tell how much carbon there is just based on this approach. Oxygen, surprisingly, you would think, oxygen is a major element. And turns out that the volatility of oxygen is simply not because it's the most abundant element in the mantle and the number one element in the whole Earth by atomic number. So we can easily put some oxygen into the core, massing up or upsetting the mass balance. And silicon is kind of a marginal, it's yes or no. That's because we don't really know how much silicon is in the lower mantle. So the bulk silicate Earth part has uncertainties. The most successful application of this mass balance method is probably sulfur. I think most people accept that the core contains about 2-8% sulfur, and that's why its volatility. So we can kind of estimate how much sulfur is in the bulk Earth, and whatever is missing from the bulk silicate Earth would be sequestered by the core. So this approach has uncertainties because the meteorite analogs, they're not perfect, especially the volatiles and some of the major elements. We actually have quite a lot of uncertainties. So what can we do? Another approach that helps us to identify candidate core models is to look at metal silicate equilibrium. This can be done through experiments or theoretical calculations. And we can look at element partitioning and isotopic fractionation, both aspects. One of the most successful outcome of this type of study is the identification of oxygen and silicon both existing in the core. This is something we wouldn't have thought if we just rely on the meteorite analog, because those asteroid bodies, they're much smaller, the pressure range is much lower. So we wouldn't be able to put oxygen into the core unless oxygen fugacity or some very special conditions were applicable. We also, for a long time, thought oxygen and silicon, they are mutually exclusive because silicon basically indicate very reducing condition, oxygen indicate oxidizing condition. But showed that oxygen and silicon could dissolve into the core together, basically a small part of the mantle dissolve into the core. So this allows us to identify a model that might be unique to the Earth. This approach, I'm showing a very nice cartoon drew by Rebecca Fisher. You heard her talk last time. This shows the core formation model. So it's a very nice approach, but there are really a lot of uncertainties because the pressure, temperature, and the composition, how they evolve through time. There's just so many knobs you can turn to adjust this process. And then it's very hard to have a definitive process that to construct based on what we know. And we also have to worry about extent of equilibrium. Even if the pressure temperature condition, how much exchange happened. So I think this is very good for identifying candidate models, but in terms of constraining the composition, it's relatively weak constraints. It's probably better the other way around. Once we figure out what the core is made of, then we can use that to learn about the Earth accretion and the core formation process. And this figure shows basically a coupled dissolution of oxygen and silicon in the core. So what we do now that we've got a number of candidate models, so we can then test these models against the mineral physics constraints. So that is very effective. For instance, if you look at the core according to the Prem model and then iron plotted over this solid line, this gray area is the core. You see that iron has a reasonable good match to the core. And we also know this famous work by Birch in 1952, inferring the presence of lighter elements because of the mismatch. You can see that the density of the core, if you look at this place, the density of the core is smaller than the density of iron. Therefore, we expect to have lighter elements in the core. But of course, this mineral physics approach alone has no way to tell what the Earth's core is made of. For mineral physics, it could be made of aluminum. We know that's not the case. So this test really needs geochemistry first to identify potential models, and then it can help refine those models. And we have studies, for instance, Fei's group has done study to say we need we cannot have oxygen there, we need sulfur. And then there are other theoretical models that, oh, we need to have oxygen. So this approach is very good. It's still in developing because we are not quite sure about the material properties yet. So at this point, we can actually already go ahead to propose a core model. And this is a model that I put out there. So what this one shows is the element abundance as a function of increasing atomic number. The red one is what is in the core, and the gray one is in the bulk silicate Earth. And we see the major elements. For the core, iron is the top number one, and then we have sulfur here, nickel here. So these we kind of have a lot of confidence. Silicon, this is a biased model, as I will show in the next slide. So we have these elements there. We don't know which one is the number 2 or number 3 most abundant element in the core, but we know iron is the number 1 element. And then there are a number of minor elements, carbon possibly, and phosphorus, chromium, and cobalt. These are probably likely. And then most of the elements in the core would be trace elements. That means that its abundance is below 0.1 weight percent. And we have all the noble metals over here, and then very little, the highly lithophile, refractory lithophile elements, they are basically non-exist. So this is a model we can put out there. Once we have this model, we could try to test it. But before that, as I mentioned, we have, even in terms of abundant element in the core, we have different competing models. All of these models, just with a dozen or so elements, you can add up to 99.9 weight percent of the core. And here we have a model that has sulfur together with oxygen. Here is the sulfur with silicon. That's the one I showed in the previous slide. And we could also have both silicon and oxygen. And because of adjustment, the abundance of iron would change accordingly. But nickel, because it's minor, it doesn't change as much, so about 5% also. So that's what we have right now. We can go on to test these models. There are a couple of ways, at least. There are more ways. I'm going to mention a couple of ways to test it. One of the ways is look at the solid-liquid alloy equilibrium at the inner core boundary. So that's between the solid and the liquid core at this boundary, which is more than 5,000 kilometers below the Earth's surface. So this model, we can test it against the temperature. For instance, if we take a composition, we do calculation or experiments, find out at what temperature it will start to crystallize. And that would be the temperature at the ICB, the inner core boundary. And then following an adiabatic gradient, we can calculate what is the temperature at the core mantle boundary on the core side. And the very base of the mantle, the temperature would be similar to that temperature. And we know that mantle, the base of mantle is mostly solid. It might have a little bit melt, but mostly solid. So you would want this temperature to be below the solidus of the mantle, range of solidus of mantle. So iron, pure iron apparently is not good enough. And when you add lighter elements, they would be anti-freeze, kind of having this anti-freeze effect. They will reduce the melting point or the liquidus temperature. And then you could test this model this way. This test could be effective for some models, but not all of them. There is a more model or test, which is look at the composition part. So again, you're still looking at solid liquid alloy equilibrium, but you want to see when the solid core comes out, what is the composition of the solid? What is the composition of the remaining liquid? So this is an example drawn for sulfur. This is only, we don't really know this phase diagram well, but as an illustration of concept. So you have the molten core coming down at this point, is going to produce a solid. And this solid has certain composition. So the solid and the liquid has to be able to reproduce the density on both sides of the ICB boundary. And that is going to be a very stringent test because we can put every model to that test if we can know the phase diagram at this inner core boundary pressure. And we can see also, for different lighter elements, they have very different behavior. Silicon, for instance, maybe the difference between solid and liquid would be so close, we can exclude the iron silicon binary model right away. And for carbon, it's also possible, depending on the temperature, it could be matching the densities, or it could be rejected just on that basis. So I know the people, both Mike and Fei, they've worked on this problem. And Rebecca also had results on iron silicide. So this is going to be a very useful test. So just to help myself organize all these different constraints and according to for the Earth core model, I have put together this kind of diagram. So you see there are observations over here. These observations include the magnetic field, seismic, and other geophysical measurements, how you measure the average density of the Earth, seismic like shadow zone. And then the other type of observation would be the geochemical and the cosmochemical observation, including the Earth's crust and the mantle and the meteorites. And here we have material properties that we would measure or calculate. And here we have core models. This model represents the physical properties. It is molten, what is the pressure density? Basically, Prem give us this information. And then here we have these different elements we want to figure out. And there is temperature formation. I have the double arrow to show that these things actually mutually constrain each other. So we have to iterate between them. And here, all these different lines shows, phase diagram, it can give a very good constraints on temperature and possibly to the amount of oxygen. But other things might have, for instance, transport properties. It does not have very strong constraints, but they can mutually inform each other. And I want to emphasize that there are three kinds of constraints over here. Some of them are very good at identifying the candidate models, for instance, the mass balance and the chemical equilibrium. And some of them are really good at screening candidates, those density, velocity, phase diagrams. And then there are still this type, for instance, Earth accretion and the differentiation. I think these are probably better suited for exploring implications because there are just so many possibilities, so many uncertainties over here. So it might be more useful once we know the composition, we could put constraints on the accretion and differentiation. So I want to mention Fuatera because several years ago at AGU, I was presenting a poster on constraints on from neutrinos, and he came to my poster. He said, "Tell me what it's made of. I'm getting old. I really want to know." And I thought, I cannot really give him a definite answer, but I want to also reflect on that and encouraging that in just a little bit over 1 century, we have turned the problem from enigma to a conundrum. Of course, I also did not know the difference between enigma and a conundrum, but the conundrum is like a puzzle or riddle that is probably at least solvable. That means we have so many observations right now. If we can identify a model, and then that fit all the observations, then we would have pretty good confidence that that is our answer. An enigma may or may not, some kind of mystery may or may not be solvable. So I think at this point, we actually have a conundrum, no longer an enigma. So because we have very good pressure, temperature, and composition coverage, both through experiments and the theory. And the issue right now is that the data quality has to be improved because we see a lot of inconsistency between experiments, between theories, or between experiment and theory. But these seem to be a solvable problem. If we keep working on this, then we would be probably able to come up with an answer. So I think that would be my answer to Fua's question about the composition of the core. So at this point, I'm going to switch to the second part about carbon. Is for most people in the audience, many of you probably can speak more eloquently about why carbon is important and interesting. I just want to mention a couple of things. One is that carbon is the number 4 most abundant element in the solar system. So aside from hydrogen and helium, which astro people call them metals. So among non-metals, carbon is number 2. There are a lot of carbon around, and it makes the backbone of life. So it's a life essential element. And people also know about, right now, Earth Day, we worry about global warming and climate change. And carbon, the CO2 is a problem for us, but we also want to remember that without the CO2 and other greenhouse gases, the Earth's surface would be -1 degree Fahrenheit. That is the temperature of deep freezer in a household, instead of this average 59 degrees we have right now. So the greenhouse CO2 actually is very important even for reaching a good temperature. We just need to have the right amount, not too much, not too little. And we don't really know in terms of the bulk Earth, how much is too much, how much is too little. But carbon is very interesting. And my interest in studying carbon in the core actually can trace back to my years at Carnegie. I remember Bernie Wood came over to visit, gave a talk. And just a few years before his visit, he published a paper on EPSL, making a prediction that the inner core could be made of carbide. So his prediction, I found it to be really cool because right condition, we know that iron and carbon has a binary eutectic system. The eutectic point is about 4 weight percent carbon. But based on thermodynamics, he predicted that this eutectic point, once it reaches the inner core boundary pressure, it's going to shift to so close to the iron end member that even if you have a tiny amount of carbon in the outer core, the first phase to crystallize this solid inner core would be a carbide. So I thought, yeah, we can test this model. Why don't we make some carbide and put it into diamond emerald cell, squeeze it to see if it matches the seismically and geophysically derived density and velocities. So I went on to do this work, and after I left Carnegie, I continued to work in this area. We do this diamond emerald cell work. Initially, we measured the equation of state, and later on, we measured the phonon density of state, which give us a way to calculate the sound velocities. So this is a graph to show that iron carbide, that actually within uncertainty has a pretty good match to that of iron at the relevant condition. What is really intriguing is that this iron carbide among all the candidates are the most outstanding ones to be able to match the very low shear wave velocity in the inner core. And we also have seen other groups confirming this Poisson's ratio of iron carbide is particularly high for reaching the liquid kind of value. Of course, I know that Linduka is in the audience, and she's the speaker for next week. And I know that we worked on this in parallel, me on experiment and she on theory. We have actually reached the opposite conclusion. So you get to see both sides of the story through this series. Is a to have a series. So, but anyway, so we did this test. Our conclusion is, yes, it works, but it works only if you have this composition of the core on this carbon-rich side of the eutectic, right? So we have to test Bernie's prediction, whether this eutectic point really gets to very close to the iron end member. And that test has been performed by many groups, including Mike Water, including Fei and other people, and also theories. So up to this point, it seems that we probably get to 2% of carbon for the eutectic composition. That means you need to have at least 2% in order for the carbide to crystallize to form the inner core. So then the question becomes, do we have 2% carbon in the core? So Bernie, myself, and Annette, I think Annette is also, I saw Annette there in the audience as well. We worked together, wrote a review paper, which is published on this review of mineralogy and geochemistry, edited by Bob Hay. And in this paper, we said there is probably less than 1 weight in the core. The upper limit is probably 1 weight %. And that's essentially, there are a lot of arguments, but the key argument is, again, based on the mass balance. So now I've turned this around to put carbon on, on the left, on the up and front. So what we see that carbon, this half mass condensation temperature for carbon, there's a wide range. That's because carbon is highly volatile. So this condensation temperature is low. At this low temperature, the kinetic inhibition becomes important. So we actually don't really know this. There's an order of magnitude variation in terms of what is the temperature for carbon. But we could take the upper bound, like 626 is one of the proposed values. It's almost like sulfur. So we would say the upper bound for the bulk Earth would have a carbon to sulfur ratio that is like the chondrites. If we take this value, doesn't matter how much it's in the bulk silicate Earth. Now that value also varies by a factor of 5, as shown over here. But this does not really matter. This gives us, we take this lower value here and this upper value over here. We get to the point there will be 1.1 weight % of carbon in the Earth's core. So unless that eutectic point get to that low level, then maybe carbide wouldn't be this inner core composition. So I showed this to my colleague, Ted Bergen. So this is the team of the second part of my talk. So we have Ted from Michigan, astrochemist, Jeff Blake, Caltech, is also astrochemist. And we have Fred Chesla, who does the modeling, and we could classify him as a cosmochemist. I know he had worked together with Connell and Larry at the EPL. And we have Mark Hirschman, who is another geochemist, mineral physicist. So as a team, we call that INSPIRE team because we had a grant from NSF between Astro and the Geo. They had this program for a while. So I talked to Ted. Ted is astrochemist, and he basically looks through telescope into the sky and look at the nebula disks. When I look through microscope into dust, right, look into the interior, we are just very opposite. So when I told him about this model, he said no. He shook his head, said that this does not work for carbon. And his reasoning was, when they looked at, this is one of a test student, they look at the remote distant disks, they see CO in the gas. CO is what they found to be the main carbon carrier in nebular gas. So that tells us when dust sublimate, they will make CO. And CO condense until 41 K. So that's very low. Earth right now, we have 300 K, 41 K is just the Earth probably never experienced that temperature as a planet. So then this half mass temperature would become meaningless because these carbon monoxide will never come back to make half of the gas and half solid state. And then also Ted referred me to the work by Nebular, so Connor and Larry, they and other people also on the list, they found that the carbonaceous, those solid carbon, they form during the death of stars. So these are the pre-solar material inherited from other stars. They're not product of condensation from a hot atomized nebula. That means the CO, once it gets to the gas, it doesn't come back to make these kind of organics that we found in meteorites. And that implies that sublimation is irreversible. You lose carbon to the gas, it becomes CO, and the CO does not come back until much later. It doesn't come back as in another form, in this organics either. So if this is the case, condensation model does not work, then what works? So if we look in the meteoritic records, we look at comets and chondrites, we see that they contain quite a lot of carbon. Most of them are the organics, carbonaceous organics, and they are depleted relative to the interstellar medium by different extent. So this kind of depletion is understood in terms of a soot line. This was proposed by Kress in 2010. The way soot line works is it divides the area, the region where the carbon-rich grains are stable. Behind the soot line is stable because it's cooler. In front of soot line, these carbon-rich grains, they would be destructed. They will be destroyed and get lost to the gas. So this soot line, probably people know about the snow line, frost line, and so on. This is different in the sense that the snow line is about formation. Usually we think about the formation of snow or ice, but soot line is about destruction. You lose it, and that's it. So then based on this concept, we think that the carbon, the behavior of carbon should be governed by sublimation sequence rather than condensation sequence. So we place the sequence over here. At the very low temperature, you would have these ices, so carbon monoxide, carbon dioxide, methane, and methanol. These would make up 50% of the very volatile, the ice phase, which get evaporated first and become the gas. That's the CO gas, we observe in the nebular gas. And then we have these aliphatic and aromatic organics and then more refractory organics. These organics, they don't get evaporated until about 500. So there is a temperature 500 where you lose most of these things, majority of them. Then you eventually come down to just a very little refractory amorphous carbon or silicon carbide, those components, the more refractory ones that can survive those sublimation. And at this point, I really want to thank Larry, who reviewed our paper and then made us think more deeply about the concept of the soot line temperature, because we cited a temperature of 425 from literature, and we thought we'll go on with our research. But Larry asked us, how is this temperature valid? So we went through more rigorous definition based on the kinetic rate law, and also validated it through experiments. These are experimental results and observational results, and George Cody, all from this lab. So I'm talking to an audience who actually know more about this type of science than I do. So we were able to define the soot line temperature. We find it to be like 500 K. We adopted this value. And then once we know this 500 K soot line value, we want to look at what happens in the solar nebula during the formation. So we very conceptually have this molecular cloud collapse into a disk, and the disk is viscous in the beginning during the accretion of the sun. And then as the accretion rate decreases, it becomes less viscous, and finally it has this point become a radiation a disk, which means the sun is already born, it's shining, it's no longer growing significantly. So we can model this thing. That's what Fred Chesler did So we model the soot line as a function of time. This is a log time. So this one marks 1 million years. And here the red one is the viscous disk with the error uncertainty envelope. And then the blue dashed line is the irradiated disk. That means a disk which is no longer growing. And we use this formulation, which accounts for luminosity that differs from R and different flaring angle. And there's a constant over here. So for the viscous disk, so this happens early time, it's accretion dominated, and the irradiated is it happens later. For within a disk, it happens later, it's radiation dominated. So what we see over here is this is 1 AU. That's where the Earth is nowadays. And then by 1 million years, this is the before the birth of the sun. By 1 million years, even in a viscous disk, in many of the cases, the soot line would have already crossed the 1 AU. In an irradiated disk, the soot line is very close to the star. So we illustrate this in this cartoon over here. In the accretion dominated disk, the soot line started probably from tens of AU and then it moves inward, reaches maybe a few AU, and that's where some of the loss happens registered by meteor chondrites and comets. And then by the time of 1 million years or so, the soot line would be moving so close, way past 1 AU. So anything that comes to Earth's orbit at that time would be loaded with carbon. So what this tells us is there is a very early window for carbon loss in the nebula disk. If you want to get rid of carbon, you have to do it within a very short time window. So then Ted would ask me, he said, how much carbon can you into the Earth? What is the maximum carbon you can put into the Earth? So we can do this. This is kind of a child's play from physics people's point of view, because right, we're just saying, okay, let's say aside from iron, all the light elements is carbon. So how much carbon can we put there? So we just do this very simple density match. We found that we can put probably 5% carbon there. If you have 5% carbon, you would be able to account for the density deficit in the liquid outer core. And if you calculate that to the bulk Earth, because the core is 1/3 of the Earth, we get that a very generous upper bound of 1.7 weight percent. That's less than 2% in the bulk Earth. And then probably is less than half a weight percent. So we get these kind of information. Now we put it back to this figure. So what does it mean? The Earth is highly, has very strong carbon deficit, is highly carbon poor. So we lost 94 to 99% of carbon that it was originally in the pre-solar grains. That's the bound over here, the generous bound and the probable bound. And that basically tells us or lead us to this conclusion that Earth's carbon deficit has to be caused by early through irreversible sublimation once it's lost there. Maybe I should say it's not, has to be, this is a way to explain carbon's deficit. And then I know that Mark will probably be visiting you soon, and he will tell you other possible loss mechanisms. So, but the Earth does have carbon. We know that for sure. Even the mantle has at least 100 ppm. The core probably has similar amount or more. So how did Earth get this carbon? And we are proposing that based on this sublimation sequence, we think those carbon are inherited directly as from a pre-solar grain in the organic, carbonaceous organic forms. It's everybody knows that carbon as an element comes from dust, from other stellar. We don't make carbon in the solar system. But we think that even stardust literally comes basically to Earth in the form of organics, because otherwise it wouldn't be able to accrete to Earth. That's why we have this, we had fun release this press release about stardust to pale blue dot and how carbon, the organic carbon have survived an interstellar journey to arrive on Earth. And people probably know that the pale blue dot was a term proposed by Carl Sagan. Many people thought stardust also came from him, at least I thought so, until Mark told me that this was actually already there when Johnny Mitchell, I did not know Johnny Mitchell, but And indeed, she already said this back in 1969. And I'm going to, just for the fun of it, play a live video for just a minute of the song, what she said.
Well, everybody has heard about Woodstock, and maybe a lot of you were there. There's a song called Woodstock, and has a chorus that goes, "We are stardust, we are golden, and we got to get ourselves back to the garden." That's all. We are stardust, we are golden, and we got to get ourselves.
Okay, so billion-year-old carbon. And we are called in devil's bargain, but we need to get back to the garden. So I thought that was kind of fun to understand the stardust better. So now it comes to, I'm going to conclude what I talked about here, the Earth's core composition. We have changed this problem from Enigma to Conundrum in just over a century. And all the constraints on core composition, they're not equal. Some of them are good for identifying models, and especially metal silicate equilibrium at a megabar. These are critical for identifying core model for Earth. And some of them are good for testing models. We can look at density, velocity, the average value, and then the depth dependent value, and the behavior, melting behavior at the inner core boundary. These would allow us to select from all the potential models out there. And then once we figure out what these models are, we could learn more about how Earth acquired its volatiles and how the core formed. Of course, this is an iterative process. They can inform each other to some extent. And there's still, at this point, a very large uncertainty in the light element composition of the core. So, but we do have a lot of the capability nowadays to study material properties at extreme conditions. These will hold key and a promise to an answer. And for the second part, I show a interdisciplinary study that combines geo, cosmo, and astral constraints. And we basically point out that the carbon acquisition by the Earth is governed by sublimation rather than condensation. And based on the fact that the soot line moves inside the Earth's orbit in the first million years of solar birth, according to the model, and then the Earth is very carbon poor, we conclude that most of the building blocks of Earth lost the carbon very early on. And we also out that Earth probably inherited its carbon from pre-solar grains. That's because those carbonaceous organics, they are the main carbon carriers in the dust. And once they get sublimated, they never come back. So, well, not never, but not for Earth because the temperature is too low and the kinetics does not bring it back into this form. So then we infer that the Earth inherited its carbon from pre-solar. So that's all I have today in this lecture. Thank you very much for your attention. I will answer your questions.
Well, thank you very much. And it's really nice, and you're putting so much information and together a way we can understand and also can relate. And this is a very good way to set as the stage for our future discussions on this composition of the core. So this is going to be now open for discussions, and I saw Peter has hands up.
Yeah, hi. Well, thank you for playing the Joni Mitchell song. That was nice. My question is, what does your carbon story say or predict about the planets interior to Earth, Venus and Mercury?
Venus and Mercury.
And their carbon content.
Right. I think the general assumption for Venus is it has the same amount of carbon as the Earth, but it put it all out there in the atmosphere. And based on what we said, we would expect Venus and Earth, Venus and Mercury to be carbon poor as well, partly because they are even closer to the sun, so the loss would be even more severe. And I would say, yes, that if Earth has no more than 1% carbon in the core and probably less than 0.5% as a whole, I think these two inner planets would be even more carbon poor.
Dento?
Hi,
Hey.
thank you for inviting me to the seminar at Carnegie from New York. I was going to ask a question about reduction and oxidation because these are very important. We know the andesite chondrites have lots of pure carbon as a mineral in them. And we also, though, to follow up on Peter's question, we suspect very, very strongly, based on the evidence from Messenger, that Mercury had a primary graphite flotation crust. And so how would that fit in? Because it doesn't look like a carbon depleted planet, nor is it depleted in other volatiles, especially either. In fact, it may even have more sulfur. And that would be my third question. Is there also a sulfur problem based on sublimation as well? Because the sulfides don't condense to very low temperatures and then they're very kinetically inhibited. Thank you.
Right, I see. So this question basically touches upon Mercury being a very reduced body. We have looked at, for instance, in the meteoritic records, carbon does occur as, for instance, graphite and diamond, but this is very, very small amount. So, and then Ted looked into, so we look into amorphous carbon, the reduced carbon form. And right now, our understanding is these occur as very small particles, very light, very small particles. They are subject to oxidative kind of loss. So through photo process in the disk, they probably won't be able to survive. So Mercury is quite a unexpected kind of planet. And when you talk about these carbon graphite layer on Mercury, I guess in the big picture, how much does that really account for the entire planet? I haven't looked into that right now. So I'm basically thinking on my feet at this point. And you also pointed about the sulfur in Mercury, and that is something I worked on, and I know that according to the condensation model, we shouldn't have much sulfur in Mercury at all, but we usually accept the range between even up to 10% sulfur in Mercury's core. I'm not sure if I can give you any definitive answer. I think you two asked a really good question, and I'm going to look more into that. I cannot say I know an answer, this is how it works. Yeah.
Good.
Thanks,
good.
Jackie.
Any questions for the audience? While we're waiting for people to raise their hands, and I do have questions. So I really like the way you kind of put it into different constraints, different data that they have play a different roles in terms of constraints, composition of the core. And but I do want to raise the question is in terms of uncertainties. In the end, you kind of says, well, we will have a definitive answer in the light element core, but that's in terms of testing model, really rely on the accuracy of the measurement. So if you look at all the data that's published in correlation with, the amount of the light element and just take a density, that's the best that we can measure in so far. And really what kind of accuracy we need and to definitively, put a number in terms of compositions. Yeah,
I fully agree with you. Actually, I think I even said that that's the data quality, right? How well we can constrain them, that's the key. But I do think that is a solvable problem. Conceptually, we could get there by having better data, more consistent, and that people agree upon. And so I think that just from a conceptual point of view, we have hope to find it. Not like we don't even, before seismology, we don't even know the size and the shape. And before the diamond anvil cell, this extreme condition, we wouldn't even think about the silicon oxygen. I think we've passed the conceptual stage. We are working on getting the details right. Well, it's important details, but I think this is accessible. The answer is accessible, at least.
Yeah, good. Thanks. And I see Rudy has a question.
Yes, wonderful performance. I enjoyed it very much, and this is all very interesting to me. But my question is, if all of these conundra and enigmas and so on got resolved, how would it benefit us all?
How would it benefit us all? I think, okay, so my very first slide was trying to address that question, why is it important? But maybe you are thinking about something more specific. So for one thing, that the team that I'm working with right now, we are thinking about exoplanet. How do we apply these kind of understanding to examine chemical habitability of exoplanets when those planets formed in different kind of stars, when they have different sizes and the mass and composition? How would this process affect, influence the formation of these bodies, and how often they form, how likely they are going to be habitable? Personal inspiration is, or maybe which I should call it aspiration, is trying to understand how the Earth forms and evolves the world. And I think this is part of the big the goal. So does that answer any part of your question? How does it help us all?
It's part of it, but my question has more to do with how do I explain to my relatives and friends back where I came from why this is important? Why should we want to know how to resolve these conundrums and enigmas? Because if it doesn't affect us, then why bother?
Yeah, I guess I can cite other people's example how fundamental research could benefit us. People study the structure of atoms. They study how the DNA. So in the beginning, it probably looked very remote, but now we have information that can create a vaccine for us. We can have a nuclear energy. You can have all kinds of other things that become practical. So most of the Nobel Prize winning research started before they get Nobel Prize. So usually they were doing something that's so far remote. The relativity goes to that thing that your relatives probably have better things to think about than those, but they do have impact on us actually in a major way, but in a long-term and very often unexpected way.
You're preaching to the choir. I believe it. I have to convince others.
That sounds like a good topic if you want to join us at 1:30. And I will move on to John. John.
Yeah, hi. That was an interesting talk. I'm going to ask the question which I asked when we talked about your paper recently in our reading group, which is in the soot line model that you talk about, it seems likely that the parent bodies of the carbonaceous chondrites were always outside the soot line since they appear to have formed in the outer solar system. So why is it that the carbonaceous chondrites are also highly depleted in carbon?
I think our understanding is they actually have been inside the soot line at some point, or at least some of the components were on the hotter side of the soot line, right? They lost the carbon. The way they lost the carbon is through this sublimation. That's the mechanism for carbon loss. So the soot line started very far out, but it has to move past the asteroid belt and past some of the cometary. The comets in general have more carbon, so that would be consistent with the fact that they are in general further away from the sun, and probably more likely that most of the components were soot line.
Just to follow up on that, if the carbonaceous chondrites formed outside Jupiter, which seems to be the current thinking, I don't think any disk model would have had the soot line outside of 5 AU.
In fact, okay, so I know that the soot line started actually tens of AU from the sun, so it moved in later on. So the soot line is about 500 K. So in the early stage during accretion, a very fast accretion, the soot line would be very far out. That is my understanding of how the soot line evolves. So it didn't start at 5 AU, not like where Jupiter is. Started at where Pluto or the Kuiper belt is nowadays.
Ron?
Yeah, thanks. So nice talk. Thank you. So I've always been a supporter of sublimation as being the main process in the nebula, and probably more important than condensation. But that's the thing, is that it won't just be carbon that's going to be sublimating. So all kinds of things will be going up from whatever solids there are. And so when you talk about depletion of carbon, I mean, you have to be considering the processes that are happening with all the other elements as well.
Yes, so I think the difference, I don't know, are you finished or are you still trying to?
Yeah, sure.
Okay, so the difference between carbon and many other elements is that other elements, they can come back, right? They will condense back. But carbon, it doesn't condense back, partly because it's highly volatile, partly because of the chemistry. There's kinetics going on. The kinetics would be specific to certain elements. So this is one of the major distinction. Being more volatile and it's a specific chemistry makes it the sublimation irreversible.
Yeah, well, okay, but I would say that other elements probably also have gaseous phases that are not considered in the standard condensation sequence.
That's right. The condensation model was proposed already like half a century ago. I think some people are trying to do more work. Bernie Wood, for instance, one of them, trying to understand it better. And it has a lot of, I think Denton also really knows about this quite well. It's very complicated. We probably having a first cut saying, oh, it condenses, and seem to be explaining things quite well for a long time, right? And we agree that the sublimation and condensation, these two sequences have to merge. And maybe for different elements, one would play more important role than the other. The model gets more complicated. Yes, if we really want to have a realistic model.
Yeah, I don't disagree with you. I just think that we should start from scratch and think about nebular chemistry and forget about the classical condensation sequence.
I think Denton has a comment.
I certainly will. I would note that it's, that the kinetic models must, in infinite time, yield the same result as an equilibrium model to first order. Do you agree with that, Rob? You were my TA for this stuff way back when. You realize that.
Yeah. But do I agree with that? Infinite time is a long time, so I guess it's kind of.
Well, at least at high temperatures and densities, the parts to the left of the diagram that Jackie has up should at least down to about a condensation temperature of, say, 1,000 Kelvin in the densities of a disk. Should at least
you don't have infinite time. I mean, the temperature is dropping, and at some point everything's frozen in. So. But
we don't have rate laws for the interaction of catalyzed dust reactions to make things happen at 300 Kelvin.
Okay, I'm going to invite you to come back at 1:30, and I would like to give the postdoc the opportunity to discuss the topic with Jackie. And thank you, Jackie. This is really a great talk, and hope I'll invite everyone who is interested in the topic to come back on the 1:30, the same link. And so for now, I'm going to log off and let the
I will be
postdoc
talking to the
speak.
postdocs.
Great, thank you, everyone.
Thank you, everyone.
Thanks, Jackie. That was a great talk. I actually had a question, but I recently upgraded my Zoom and I can't figure out how to raise my hand anymore. but I'll talk to you at 1:30.
Okay, cool.
Thanks, really wonderful.